My name's Dan Wells. I'm the National Consultant Specialist for Spirax Sarco in the UK and Republic of Ireland. And I presented a number of CPD presentations previously at the invitation of Engineers Ireland. However, today's presentation topic is on the subject of an introduction to steam condition in the pharmaceutical sector. So just a quick introduction to Spirax Sarco. We're a team that's approximately 200 strong. Approximately 12 of my colleagues are based over in the Republic of Ireland, and they're available to assist should you require any assistance, either on your site or in your offices. More than happy to offer support. We've also got a lot of very, very useful calculators and configurators that are available for reference on the desktop version of our website. Calculators, configurators, tutorials, and so forth. But I'd also like to draw your attention to our Spirax Sarco app that can be downloaded both to your iPhone, to your Android phone. It's free of charge to download. And there's a similar, very, very powerful suite of calculators and configurators that may be of some use to you. So today's presentation, as we can see, we're going to look at an introduction to steam condition in the pharmaceutical sector. First of all, we're going to look at how steam is generated to understand the potential contaminants that steam can pose to the process. And we're going to understand what constitutes a poor condition of steam and how and why different processes are likely to have different steam condition requirements. So the slide that you can see on the screen at the moment is one that some of you may have seen before, and it refers to what we know as the steam condition triangle. So at the very bottom of the triangle, you can see that we start with the vast range of processes where an excellent condition of steam isn't that critical to the process. For example, if we're looking at a closed loop heat exchange system where we just maybe add in some heat energy onto the secondary side, where there's very little risk of contamination to the process. And we can then move up the steam condition triangle, and we can look at what we refer to as filtered steam, which is typically where the steam is treated by being passed across a fine micron stainless steel filter element and a filtered housing. And then we can move further up the steam condition triangle where we move towards the cleaner grades of steam, clean steam, also referred to as chemical-free steam. That's typically where steam is generated in a dedicated steam-to-steam generator. And then at the very, very top of the steam condition triangle, we've got pure steam, sometimes referred to as process steam, that is typically used in a very small number of processes, typically where we may be manufacturing vaccines, for example, for injection into the human body. Now, before we understand the condition of steam and how steam condition is important to the process, I think it's important to go back to understand the basic properties of steam. We need to go back to the fundamentals to understand exactly what steam is and to understand how and why we need to treat it completely differently to any other source of heat energy. So first of all, unlike water, for example, steam's a gas and therefore it's compressible. So that tells us that the steam moves around the network in accordance with the pressure drop. And that means that the pipes must be sized accordingly. We also know that there's a proven temperature to pressure relationship that we can rely on to determine the condition of the steam at the process. And the steam tables explain how steam has got significantly more usable energy per unit than water. And we also know that steam gives up its heat energy by condensing. So it gives up its heat energy very, very quickly, but it also gives up its heat energy equally and evenly across the entirety of the heat transfer surface area. So all of these points are fundamental to how we design a steam system to ensure that the steam arrives at the process at the best possible condition. So I'd like to move on now to look at what we refer to as the steam tables, as you can see down in the bottom left-hand corner of the screen. And then we're also going to quickly look at what we refer to as the temperature enthalpy curve that's demonstrated towards the right-hand side of the screen. So there's a lot of very, very powerful and important information demonstrated in the steam tables. First of all, we can see the pressure-temperature relationship. So if we understand the pressure that the steam is either being generated at in the boiler, distributed at in the distribution network, or condensed at in the process, then we understand the temperature that the steam has. For example, if we're generating steam at 0 bar gauge, the boiling point of the water is 100 degrees, and therefore the temperature of the steam is also 100 degrees. The next three columns that we can see, that's the energy content of the steam. And the final column, that demonstrates the volume that that mass of steam occupies at the given temperature. So I want to look at the energy columns first of all. We know that water's got a specific heat capacity of 4.19. In other words, if we want to increase 1 kilogram of water by just 1 degree temperature, we need to add 4.19 kilojoules of energy to it. So if we want to bring water up to boiling point at 0 bar gauge, 100 degrees, well, the water needs to contain 419 kilojoules of energy. We refer to that as the specific heat capacity. But we don't want boiling water, we want steam. So we need to add a further energy content to that boiling water in order for that boiling water to change state from a liquid to steam as a gas. We refer to that as the latent heat or the enthalpy of evaporation. So the interesting thing here is that when steam condenses at the process, it gives up some of its energy, but it's only actually that latent heat, that sensible heat that we added to the boiling water that passes into the process. So that means that what is left behind in the condensate, the byproduct of heat exchange, is the sensible heat. It's the same energy content that we put into the water to bring it up to boiling point. The condensate is hot water. It just doesn't have anywhere near as much heat energy in it to satisfy the process. So if we move across to the temperature enthalpy curve, that shows the journey that water takes as it changes state to produce steam as a gas. So using the example of 0 bar gauge, where we know that water boils at 100 degrees, we can see that the evaporation process is only going to begin, steam is going to start to be produced, but only when we've added 419 kilojoules of energy into it. And if we follow the axis across horizontally, you'll see that the evaporation process ends, but only when we've added 2,257 kilojoules of energy into it. So let's say, for example, we weren't on top of producing steam optimally in the boiler house, or it could well be that we got a contaminated source of fuel. If we fail to put the full latent heat, that's demonstrated on the blue line here, into that boiling water, then the water would be unable to fully evaporate and produce a mass of steam that we'd refer to as dry saturated. That's critically important when it comes to understanding the steam condition, dry saturated steam. So first of all, that term saturated, it means the steam's saturated with energy. The steam cannot contain any more energy than 2,676 kilojoules in the example of 0 bar gauge. Can't contain any more. And dry, well, it means that there's no moisture entrained within the steam. The steam is fully dry. It's got a dryness value of 1 or 100%, for example. So let's say, for example, we didn't put the full 2,257 kilojoules of energy into that boiling water. And let's say the steam existed at this point on the curve in what we'd refer to as the wet steam zone. Well, the first problem we have with wet steam is that we distribute steam as a gas some considerable distance around the network. It could be hundreds, if not thousands of meters. The wetter the steam, the more likely that steam is to condense out in the distribution pipework. So of course, that's going to result in an inefficiency. For example, let's say we were generating 10,000 kilograms per hour steam in the boiler house. And let's say we got a process in the plant room, thousands of meters away, that needed 9,800 kilograms per hour steam. Well, if we were losing 400 kilograms per hour as the steam condensed in the distribution pipework, then it's highly likely that there's going to be insufficient steam to satisfy the process. The process time could extend and extend, or we could fail to hit the required process conditions altogether. And if we've got more heat loss and more condensate that exists in the distribution pipework, well, we need to get rid of it. We can see that there's far, far less energy contained within the condensate than there is in the steam. It's of no use to us. We need to get rid of it. And the greater the heat loss and the more the condensate, the more steam traps we're going to need to install to remove that condensate. So we've got a greater capital cost and a greater operational cost because we're going to need to maintain those steam traps on a regular basis. And if we don't do that, then that standing condensate is likely to cause erosion, corrosion and rusting of the pipework and other components. And if we're distributing the steam at a fast velocity, it means we're highly likely to get erosion as the steam is conveying the entrained moisture across sensitive areas such as control valves and flow meters. And if those control valves start to erode, then it means that we're getting a very, very inaccurate and unreliable release of energy onto the process. But it also means we've got a solution that will need maintaining periodically. A lot of condensate that's held back in the distribution pipework. Well, if we get fluctuating pressures, it means we're likely to get water hammer, that crash bang water hammer effect to the pipework itself. And any dry steam that is passing across a trapped mass of condensate, it's likely to degrade. So we're going to have a number of issues here by generating wet steam. For one, we've got the inefficiency, the heat loss. We get a reduced mass of steam finding its way to the process, extension to the process time. The steam that does find its way to the process is going to be significantly wetter. It's going to have less energy contained within it, causing the process time to extend further still. We get the maintenance issues. We get the unreliability of the capital equipment, such as the control valve. We get corrosion, potential for contamination in the steam itself towards the process, and also we get the health and safety issues imposed on the network as a result of that water hammer. So wet steam is by far and away the biggest problem that we come across whenever we're talking about understanding steam condition. So there's another physical property that we can take away from the steam tables, and that's the pressure-temperature relationship. So for example, if we're generating steam at a nice high pressure in the boiler, we know that if water boils at 10 bar gauge, the temperature of the boiling water is 184 degrees, and therefore the temperature of the steam is 184 degrees. But if we only require the steam to exist at, let's say, 132 degrees at the process, well, that pressure-temperature relationship demonstrates that we can achieve that temperature simply by manipulating the pressure or reducing the pressure to 2 bar gauge. But the other thing that the pressure temperature relationship shows us is not only the pressure temperature relationship of the steam, it's also the pressure temperature relationship of the condensate as a liquid. The reason being, well, when steam gives up its heat energy, there's an exchange of that latent heat. The condensate retains the sensible heat, but the temperatures remain the same. So that condensate that exists in the distribution pipework at 10 bar gauge, it's sat there as a liquid at 184. The condensate that's sat there at the process at 2 bar gauge, it's sat there as a liquid at 132. The condensate can exist as a liquid at that high temperature because of the pressure. And the steam tables also demonstrate the pressure volume relationship. 1 kilogram of steam at 0 bar gauge, it exists at a volume of 1.673 cubic meters. In other words, it exists at a volume that is 1,673 times greater than a kilogram of water. But when we're distributing that steam under a high pressure, let's say 10 bar gauge, we've been able to compress that mass of steam down so it occupies a much, much smaller volume. However, when we've reduced the pressure of the steam at the process, we've removed that compression. So the steam is going to expand and exist at a far, far greater volume. So moving away from the fundamentals and the basic principles, when we're talking about understanding the steam condition, it all comes down to what we're actually using the steam for. Is it going to be used for direct injection purposes? Is that steam going to come into contact with a product or an atmosphere? Or are we going to be utilizing that steam in a closed loop heat exchange system where the risk is very, very minimal? Well, steam condition, it really depends. It's going to mean different things to different people. For example, a plant steam or a utilities engineer is typically going to mean that they want the steam to be as dry as possible and as clean as possible for reasons we've gone through. Whereas at the process, we're going to be measuring the steam quality on a completely different set of criteria, such as BS-EN 285. And that's where we're going to want to impose certain values on the steam condition. We're probably going to want the steam to be 95% dry or better, because an excess of moisture in the steam means not only do we have less energy than we may expect, it also means there's a risk that we could be contaminating the product or atmosphere with an excess of moisture, and that moisture is going to have boiler chemicals entrained within it. We're going to want the steam to be free of air and other non-condensable gases because of the insulating effect that air can have. We're going to need the steam to exist at the correct pressure, temperature, and mass flow to satisfy the process. And of course, we're going to want to ensure that we're not contaminating the process with any rust or scale that can arise as a result of that erosion and corrosion that we've spoken about. So steam condition, steam quality, and poor steam quality, it's really got its foot in the boiler house itself, and it's vitally important to understand and appreciate how we're generating steam if we want to understand the impact that a poor condition of steam can have at the process. So we really need to go back to the boiler house, which is, of course, where steam is generated. So Spirox Sarco don't actually manufacture steam boilers themselves, but we do manufacture the components, the ancillaries and the controls that are shown on the screen in blue here. And they're typically involved with ensuring that steam is generated responsively. So steam's there and available whenever the plant's got a demand, that steam's being generated efficiently from an energy perspective, that steam is being generated safely, but most importantly, that the steam is being generated at the best possible condition. So I'm going to skip around some of the components that you can see highlighted in blue, but even before we get to the boiler house itself, it's important to understand that the raw ingredient of a steam system is water. It all comes down to the condition or the quality of the raw water that we're being used. And if we're using a poor condition of water, if we've got poor water treatment in the boiler house, we're never going to get a good condition of steam being produced, regardless of how sophisticated the controls of the boilers are. So the map that I'm showing at the moment, hopefully it demonstrates that we could have two physically identical processes, identical controls in the boiler house. But these sites could be located 20 kilometers apart. And it could well be that one site's using an excellent condition of raw water and one site's using a poorer condition of raw water. And this would mean that the consistency in steam, the energy content of the steam, the energy inefficiency of site, for example, could vary considerably. So it's really just to stress the fact that it's critically important that the water treatment regime is matched to the quality of raw water in the given area. And perhaps the next most important component to ensure that we're getting an accurate and reliable generation of steam in the energy center and an excellent condition of steam for the process is what we refer to as the hot well or the atmospheric deaerator. And this is where we recover all of that valuable hot condensate too, typically with the aim of keeping the water at a temperature of round about 85 degrees. The benefit being, well, if we're putting hot water into the boiler's going to respond more rapidly whenever there's a demand for steam. We get less thermal shock on the boiler. It also means that we need to consume far, far less fuel whenever we need steam. But one of the benefits of keeping the water in the hot well at 85 degrees or thereabouts is the fact that we will have purged off quite a lot of the oxygen and non-condensable gases at that high temperature. And oxygen and non-condensable gases are a huge problem for steam boilers because that's what creates a lot of the pitting and corrosion of the boiler itself. So we would typically add a small amount of boiler chemicals to condition the water at this point here with the purpose of polishing off that last remaining oxygen content. But if we've got a hot well that's sat at a significantly lower temperature, 50 or 60 degrees, for example, then we've got more stress on the boiler. We've got a greater lag until steam can be produced. We're consuming more fuel and we're going to need a greater chemical content of the water to address the oxygen. So perhaps one of the first things we want to do when we're understanding the condition of the steam that is being produced on our site is look at that temperature gauge. If it's there at 50, 60 degrees, then we know that the steam is going to exist at a lesser condition than if it was sat there at 85 degrees, for example. And the next series of controls to look at is the boiler level controls. There are a number of different level control types. At the lesser sophisticated end, we've got magnetic floats. Somewhere in the middle, we've got conductivity probes. And then at the most sophisticated end of the scale, we've got the capacitance probes. They're all going to need testing and supervision of some form. The most sophisticated capacitance probes enable us to move towards a semi-automated or even an automated boiler house. Whereas if we've got magnetic level control floats, they are going to need a much, much greater daily testing and inspection regime. And the purpose of the level controls, it's to call for water in order to keep up with equilibrium of steam production. And also to send an alarm to shut off the boiler or the feed pump or the burners when the water reaches either a dangerously high or dangerously low level. Now, a magnetic float and a conductivity probe can only send a signal to an on-off feed pump. And an on-off feed pump it's easy to install, it's cheap to purchase, but its limiting factor is that there can be quite a volumetric difference between the water from the low point to the water at the high point. So if we've got a boiler that is producing steam at 10 bar gauge, where boiling point is 184 degrees, if we're bringing water from the hot well at a very, very low temperature, 50, 60 degrees, that huge mass of water being brought into the boiler is going to create a lag or a fall off in the steam production rate. And that may cause problems for the process, for the production. But it also means that the boiler's then got to take on more and more energy to get to the point where we can start producing steam. And at that point, the steam that is produced is going to be slightly wet. So we are going to see those erosion, corrosion, water hammer issues. We're going to see steam with less energy contained within it. So it's far better to move away from the simple boiler level controls to a capacitance probe, which is capable of sending a signal to a modulating pump. And the benefits of using a modulating pump is we can be constantly drip feeding in a very small mass of high temperature water into the boiler. So it's far, far easier for the boiler to be responsive and to keep up to the steam production. It's far more efficient from an energy perspective, but most importantly, the steam that is being produced is going to be of a consistently far, far better condition. It's going to be drier. And the other controls that furnish the boiler are what we refer to as the blowdown controls. So the chemicals and minerals that we add to the feed water are going to behave in a number of different ways. Some are going to solidify and fall out as a sediment towards the bottom of the boiler. And when that happens, we need to get rid of that sediment, because if it were left to build up over time, it could move up past the heat tubes within the boiler and cause a failure. So we need to get rid of it. So we get rid of that sediment by flushing a certain mass of hot water out of the boiler on a daily basis. So if that boiler's operating at 10 bar gauge, 184 degrees, the water's under pressure. By opening a little valve underneath the boiler, that pressure drop is going to see a certain mass of hot water blasted out of the boiler, and it'll take that sediment with it. Now that sediment's got to go to waste. It's nasty stuff. We can't use it anywhere else in the process. So it needs to pass to waste via what we refer to as a blowdown vessel. And the purpose of the blowdown vessel is to release that energy in a controlled way. As we get a fall in temperature from 184 degrees to atmospheric 100 degrees, that release of energy needs to be controlled. But we also need to allow for that hot water to cool down to a temperature of 43 degrees or below before it enters the town's mains. So that's what we refer to as the bottom blowdown. There's also the TDS blowdown. Now TDS, that stands for total dissolved solids. And that's because while some of the chemicals and minerals will solidify and fall to the bottom of the boiler, some will be held in suspension. And as water is being evaporated and steam's being produced, that chemical content will get progressively more and more concentrated. And over time, that can result in a blanket of foam that sits on the top of the boiler water. If we get a fluctuation in pressures, that foaming layer can expand. And that can make it very, very difficult for the level control probes to understand where the true water level in the boiler is. It also means that that foam, it's an indication that we're likely to see a little bit of scaling, a buildup of an insulating layer on the heat transfer surface areas, resulting in an inefficiency. But it also means that that foam can be drawn out into the distribution pipework. And that foam is going to contribute to that wet steam. It's going to be very sticky. So of course, we're going to get that erosion, corrosion, water hammer that we've spoken about. But that foam can also dry out and produce a very fine chalky scale. So that can contribute to erosion of sensitive areas. It can bind itself to heat transfer surface areas as well. But it can also be injected directly into a product or a process whenever we may be using steam for direct injection purposes. So it is a point of contamination there. So we want to keep the TDS to a predetermined level that is typically prescribed by the boiler manufacturer by taking a sample of the water from the side of the boiler on a daily basis. We put conductivity probes across that sample. High conductivity, that's an indication of a high concentration of TDS. It tells us we need to bleed some of that water away to waste. The problem is, well, in exactly the same way that we don't want to bleed too much water from the bottom blowdown or the TDS blowdown, if we do so, then that can result in not only an energy inefficiency, we've got to replace that hot water with more cold water from the hot well. We've got to bring that water in the boiler back up to boiling point again. So we're going to get a lag in the steam production. The problem is, as we're racing to get the steam boiler up to temperature and pressure, we are going to be producing wet steam to start off with. So we're going to get all of those issues that we've spoken about. But I just want to show a very quick image here that shows you the effect of that foam being produced. As we get a slight fall in boiler pressure, then the foaming layer is going to expand. and the foam is going to get dragged out of the boiler into the distribution pipework. That high TDS level is an indication of a lot of foaming and scaling being dragged across into the network that can cause problems, not just in the distribution pipework itself, but also at the process. So one way that we can address high TDS levels is by moving towards a pressurized deaerator. So whereas a typical hot well can only hold hot water at atmospheric pressures, temperatures of 85 degrees or thereabouts, by pressurizing the deaerator, we're able to elevate the temperature to 100 degrees and above. So of course there's an energy cost saving. Of course the boiler is going to respond more rapidly. There's going to be less stress on the boiler. From a steam condition perspective, it means that we need far, far fewer chemicals to be added to the feedwater to scour off the oxygen and the non-condensable gases. We'll have done that by using the pressure and the temperature of the water alone. So we can calculate a payback in terms of minimizing the chemicals required very, very easily. But it means that we will end up with a condition of water and therefore a condition of steam that is consistently better. The good news is those controls, the level control probes, the feed pumps, the TDS and the bottom blow down, they can very, very easily be upgraded so that we can offer them the highest level of automation to ensure that the minimum amount of blowdown is being performed. And that's going to help us not only minimize any energy inefficiencies, it's going to help us to ensure that the steam condition that is being produced is of the highest possible quality. So once the steam leaves the boiler house, it enters what we refer to as the distribution network. And remember, the distribution network can be hundreds, if not thousands of meters in length. And we want to ensure that the steam distribution network is engineered to retain the best possible condition of steam. If we've put a lot of time and effort into generating an excellent condition of steam for the process, the last thing we want is for it to degrade as it travels around the network. So when we're talking about good condition, we're typically talking about the steam being as dry as can be by removing that condensate. We're talking about removing any rust or scale that may be present. We're talking about venting away any air and non-condensable gases. Good working practice to observe safe isolation of any capital equipment. And we want to ensure that the pipes have been correctly sized as well. So there are a number of different methods to ensure the steam pipes have been correctly sized, remembering that steam is a gas, so it does need to fall in accordance with the pressure drop around site. So when we want to ensure that we've got the correct mass of steam being supplied to the process at the appropriate rate, then the pressure drop method is applicable. But whenever we want to ensure that a poor condition of steam isn't causing problems with regards to, let's say, erosion of control valves, then the velocity method is applicable. And the velocity method is typically sized by taking the steam distribution pressure that we can see in the column that runs vertically here. We choose one of three different velocities, 15, 25, 40 meters per second. And then by running across horizontally, by selecting the mass flow rate of steam and then taking the line vertically upwards, we can select the appropriate pipe diameter to convey that steam in. So why have we got three different velocities? Well, it depends on the steam quality. If we know that we've got steam that is very, very wet, then we don't want to be conveying that wet steam at a very, very fast velocity, because we know we're likely to expect that we'll have not only moisture, but rust and scale entrained within it. And that can very, very quickly result in erosion, abrasion of sensitive areas, such as control valve seats. Because as soon as that happens, we've got unwanted energy being passed into the process. So we get an inefficiency, we get product spoilage, but we've also got excessive maintenance demands of that piece of capital equipment. So we can step back, we can use this information to step back and identify if that point of failure has actually been caused by a poor condition of steam or by an undersized pipework. And whilst these sizing methods may look a little bit complicated, these calculators and configurators are part of that little app that we've spoken about. So we also want to remember that steam's a gas. So we don't pump steam. It moves in accordance with the pressure drop. And it's critically important that we understand that we want to keep the steam dry. So we want to do so by observing good working practice where we can remove the condensate as a result of those heat losses at the low point around the network. And again, with steam being a gas, it's good working practice to ensure we're distributing it, observing a fall in the distribution pipework. That's going to aid the fall of the condensate to the low point, where it can be removed via the steam traps. So when we're taking the condensate out of the network, the steam traps take the condensate away from the bottom of the pipework. But when we're removing that steam from the top of the pipework to take it to the process, we want to observe good working practice and take it from the point where it's at its driest. We mentioned venting air. We want to vent air away from the steam network using a thermostatic air vent, because we know that if we've got a significant presence of air, we can no longer rely on that pressure temperature relationship. And we also know that a trapped film of air at the process is likely to result in a significant slowdown. So we fit thermostatic air vents at the process and at key areas around the distribution network. And that's really to remind us that many processors will estimate the steam temperature by taking the pressure. But of course, we know that any air that is present, it is going to result in the temperature of the process being slightly below where we expect it to be. So it's important to ensure that we get the steam to the process in the condition that it was designed for originally. And when we're talking about different heat exchange processes, we need to remember that it could be a closed loop system whereby we could be using steam for a plate heat exchanger or a shell and tube heat exchanger or a coil, at which point it's likely that we'll be using plant steam. But we also want to remember that in a certain number of processes, we may be using a higher grade of steam, because that steam may potentially enter an atmosphere or a product and be a point of contamination. So it's here, it's where we're using steam at the process. It's where steam's being used for direct injection processes. A standard referred to as BSEN 285 that's closely referenced by ASME BPE is highly relevant. It's where we want to be able to measure the condition of the steam. We need to ensure that the steam is 95% dry or better. It's 3.5% by volume of condensate or less air, non-condensable gases, and that it's free of any potential particulates. So regardless of whether we're looking at direct injection steam or plant steam, it's vitally important that we keep it as dry as we possibly can. And we do that by passing any wet steam across a separator. Any moisture that's entrained within the steam can become entrained on the baffles and condensed very quickly, where it can be taken away. The dry steam then passes downstream across a little strainer towards the process. So there are three key benefits here. One, the drier the steam, the more energy there is in the steam, the more rapid, the more efficient the process will take place. Two, it means by removing the moisture, we're minimizing the risk of erosion or failure, inefficiency on the valves. And three, if we are going to be using that steam for direct injection purposes, by drying it, we've minimized that risk. So it's at this point here, once the steam's been conditioned, that we reduce the pressure of the steam. And the reason we reduce the pressure at this point here at the process is down to that pressure temperature principle. By controlling the pressure, we're manipulating the temperature. So we can do that with a self-acting pressure reducing valve, or we can do it with a control valve. And the benefit of moving towards a control valve is it'll control the steam a little bit more responsively, accurately. And of course, we can send a signal back to a BMS or a PLC. And the biggest problems that we come across with control valves are, well, they're either oversized. And if they're oversized, it means that the seats will spend a lot of time operating very closely together, at which point we get a lot of erosion expected because the steam will be moving at a greater velocity. And other problems are, well, those conditioning ancillaries that we've spoken about are quite often overlooked. So of course, we expect to see problems with erosion of control valves at that point. Typical rule of thumb, a well-sized control valve should be approximately 2 pipe sizes smaller than the upstream pipework. So let's just look very quickly at the impact of a process here. And this really gives us an understanding with regards to how we can go back to first principles to calculate the steam demand of a process and therefore help us to size a control valve. And it all comes down to understanding, first of all, the enthalpy of evaporation present in the steam at the known pressure. So I just want to move forwards and look at the steam tables in a little bit more detail. We mentioned that we want the steam to be as dry as possible. And using the example of dry saturated steam, when it's 100% dry and saturated, it's going to have a dryness value of 1 or 100%. That tells us that it will have a heat content or an energy content of 2,676 kilojoules. But if we fail to put the full enthalpy of evaporation into that boiling water, then we would expect steam to exist with a dryness value of 0.5 or 50%. In other words, it would have 50% of the energy contained within it that the process may have been expecting. And if we add that to the challenge of having steam that is got an excess of air entrained within it, then the insulating effect of the air combined with the wet steam means that we simply aren't going to have steam that can keep up to the process requirements and expectations. But the venting of air and the drying of steam can be very, very easily be addressed by ensuring that we've got the correct conditioning ancillaries in the distribution pipework. So a typical process, that could be, let's say, the production of steam, a production of hot water from steam, producing hot water for a number of industrial processes instantaneously. So this is just one point of heat exchange that we could have on a typical steam using site. One of the first things that we want to do, regardless of whether we're utility engineers or process engineers, is ask ourselves, what is the steam being used for? Is that steam likely to be an ingredient? Is it likely to be exposed to a product or an atmosphere? If that were the case, any moisture, any boiler chemicals, any air, any rust, any scale could be at risk of entering that atmosphere. And it's at that point we want to give thought to the steam condition triangle. If there is a risk to the process of contamination, we want to move up the steam condition triangle. We may potentially want to move above the red line and generate what we refer to as clean steam or chemical-free steam. And that's basically where we're generating steam, plant steam, being run in a 316 stainless steel coil through a 316 stainless steel generator that holds a mass of chemical-free water. And by generating that steam very, very close to the point of use, to the process, and distributing that clean steam a very short distance in high-grade stainless steel pipework, we can then get a condition of steam to the process that is fully compliant with EN 285. And I just want to show you a very quick animation to give you an understanding of how we can achieve that. So thank you for that. So just moving on, it's important to understand that process engineers in particular will have certain terminology with regards to measuring or understanding the condition of the steam and ensuring that it is compliant with EN 285. And the terminology that we typically use is either purity or quality. And when we're talking about the quality, that's generally referring to the properties of the steam, such as how dry it is, the amount of non-condensable gases that are present, typically measured in condensate, and also the degree of superheat that may be present within the steam. And when we're talking about the purity, we're talking about what the steam is actually carrying. And we can typically measure the purity by taking a condensed sample of the steam, and then we can put conductivity probes against it at a known condition. And it really depends upon what the requirements of the process are. For example, if we're using steam in pure steam applications, then we're going to have a different microsiemens reading requirement than we would do if we were using clean steam for, let's say, process humidification purposes. And one thing that is quite often overlooked when it comes to understanding the steam condition is looking at the condensate side of the loop. Now, we've mentioned condensate, it doesn't have any value to the process. We need to get the condensate away because it's a byproduct. It doesn't have enough heat energy contained within it. But we can get that condensate back to the boiler house. It does have a value there. But the condensate exists whenever there's a heat loss, and that can be in the distribution pipework itself, or it can be at the process. So just to remind us, when we're taking the condensate away, we need to remember that there's a significant benefit in that condensate. It doesn't have as much energy in it as the steam, but there's that sensible heat that is retained in the condensate. So if we can get it back to the boiler house, it's helping us not only to reduce the water consumption, it helps us to reduce the amount of chemicals that we then need to add to that raw water, and it's resulting in a significant heat energy increase. So the steam traps are typically the point that separates the steam distribution network from the wet side, the condensate side. And we need to ensure that the steam traps have been sized and selected correctly in order to allow the condensate to pass at the appropriate rate. Remember, we need to get the condensate away to keep the steam as dry as possible. So there are a number of different steam trap types, and there's no such thing as a one-size-fits-all universal steam trap. They all need to be selected in accordance with their individual process that they're being used for. But when we're looking at steam trapping on the clean steam side or on the process side, then it becomes even more important that we ensure that the steam is kept as dry enough to hit that 95% dryness value. We need to drain the condensate away as soon as it forms. So because we need to drain the condensate away very, very quickly, and because we can only afford to live with the steam trap being failed in one particular position, we can't afford for that steam trap to fail closed, at which point condensate would back up, then there really is only one type of trap that is going to be suitable for our purposes. And that's the little thermostatic trap. And when we've got a thermostatic trap that's used specifically on a clean steam system, it's going to have a specific element that is very, very sensitive, and it will open very, very quickly to ensure that condensate is drained away as soon as it is generated. So it's a very, very sensitive trap. You'll also notice that unlike a plant steam system, we don't have a dirt pocket because by nature, we're not going to have any debris or particulate on the clean steam side of the distribution pipework. And we want the condensate to fall straight through the trap where it can be taken away straight back to the energy center for reuse. But steam traps, they do require a differential pressure. We need to use the steam pressure to push the condensate across the trap and energize it. Now, certain processes will only need the steam to exist at a low temperature. And if we've got a low temperature, we've got a low pressure steam. So if that pressure downstream of the condensate, downstream of the trap, is greater than the steam pressure, the condensate, it simply won't move. It'll back up, it will flood the heat exchanger, or we'll get a very, very erratic release of heat energy onto the process as a result of that backed up condensate. So it's then that we may need to give thought to a slightly more sophisticated steam trap. It's what we refer to as an automatic pump trap. And that's because it can take a mass of high pressure steam and it can add that motive energy to the condensate to drive it away. Of course, we know that there are certain occasions where the condensate's never going to have enough motive energy, and we will need to pump it away from the process using either a mechanical condensate recovery pump. That's where we use the steam pressure to drive the energy away. We don't need electrical installation there, so it can be used in intrinsically safe areas. But for other areas, we can use an electric condensate recovery pump. The thing to bear in mind with the electric condensate recovery pump is, yes, it does require electrical installation, but we also know that we can only actually pump condensate when it's a single phase liquid. And we can only pump that single phase liquid when it's at a temperature of 97 degrees or less. So we're not going to get cavitation of those pumps. So we need to size the receiver, but also the vent to allow for any excess energy to be vented safely away to atmosphere, so we're not resulting in those pumps cavitating and failing. If we did notice a low temperature in the hot well that was resulting in not only energy efficiency issues, but steam quality issues, then the first place we'd want to come and investigate is the condensate receiver and check that those pumps have not failed. But as we can see here, we do need to vent some of that energy away. So typically the amount of flash steam that is vented away to atmosphere is dictated by the mass flow rate of condensate and also the pressure drop. The greater the pressure drop, the greater the percentage of flash steam is going to be produced. And that flash steam does need to be vented away because, as we can see at the image at the side of the screen here, we know that steam exists with a much, much greater volume than condensate does as a liquid. So venting that flash steam away, it prevents the pumps from cavitating and failing, and it prevents from an overpressure on the condensate infrastructure. The problem is there's just as much heat energy in that flash steam as there is in plant steam. And it also means that we're missing the opportunity to recover as much condensate as we possibly may do. So we may want to give thought to any areas where we can recover as much of that flash steam as we can, or use it in another process. At the very, very least, we should be recondensing that flash steam to maximize the rate of condensate recovery. And you may say, well, why is that important to the process? It's important to the process because if we can get more and more hot condensate back to the hot well, not only is that condensate hot water, it's also chemically conditioned. It's in an ideal state for going back into the boiler. The fewer chemicals we're consuming, then the lower the TDS level we're keeping of the boiler, the less blowdown we're performing. So we're getting less TDS, less foam being dragged out into the distribution pipework. We're getting less steam, less wet steam. We're helping to keep the steam as dry and free from particulate as we possibly can. Now, we know a lot of clients, a lot of steam using sites will dump the condensate to waste for fear of it being contaminated. The good news is we can test the contamination rate of any condensate using a conductivity probe. And if that sends a signal to a diverting valve, that contaminated condensate can be dumped whenever it is a risk to the network. But whenever it's in an excellent condition for being reused, we can divert it back to the hot well. So there's a lot of information to go through there, and I appreciate you taking the time to bear with me this afternoon. But I'd just like to summarize very, very quickly that we're only ever going to get a good condition of steam if we're using a good condition of raw water, and if that raw water is being chemically conditioned appropriately. We also know that talking about a good condition of steam is going to mean different things to different people. It depends whether we're plant engineers or process engineers, whether we're using the steam for direct injection or in a closed loop system. On the plant side, it means a poor condition of steam. It can result in erosion, corrosion, water hammer, poor heat transfer. On the process side, a poor steam condition can result in contamination to the process. Everything starts in the boiler house. And the good news is we can increase the efficiency of the lesser sophisticated range of controls that furnish the boiler very, very easily. We can retrofit upgrades in a minimum of downtime. Please remember that wet steam and air are perhaps the biggest enemies of a well-designed steam system, regardless of whether we're talking about process steam or plant steam. But please also give thought to the value of getting that condensate away from the process and getting it back to the boiler house. So thank you very much for the time that you've spent with me today. We have got a number of further Engineers Island approved CPD presentations. Should they be of any interest, I'd be more than happy to supply you with a PDF of the slide pack that we've gone through today, and also provide you with an attendance certificate. If you'd like to reach out to me, I'll make those available to you. But on that point, I'd just like to ask Sinead if there have been any questions that need addressing at this point, and I'll gladly answer them.
Hi, Dan. Thanks very much for that presentation there. I think you covered an awful lot of ground. I have asked people in the chat if they wanted to put their questions in the Q&A. So it's, I know we're coming up to the hour, but if anyone has anything, please do put them in the Q&A box, and we just give a minute or two to see if anything comes in. But I suppose while we're waiting, maybe I have a question for you. Actually, yes. Well, one has come in here now. Actually, we can answer that one instead. So somebody's wondering, what is meant by wire drawing?
Wire drawing, basically steam valves are metal to metal seated, highly polished surface areas. If we're distributing steam at a velocity of 40 meters per second, that's about 70 miles an hour. So imagine if we've got an oversized control valve that's operating very, very close to its seats. If we've got steam with even a few specks of moisture entrained within it, moving across a control valve at such a high speed, over a matter of weeks, it's just going to gouge a line through the disc of the valve, through the valve seat. And it looks almost as though like a hot knife or a wire has been dragged across a pat of butter. That's what we refer to as wire drawing. Problem is wet steam.
Okay. I suppose I'll ask one question if that's okay, and if anyone has something else they'd like to ask, please put them in the Q&A. So I saw filtered steam mentioned in one of your slides, and what place does this have in the pharma sector?
It doesn't, is the simple answer. It's all about risk. If we put a stainless steel, a sintered stainless steel filter element in a housing ahead of a process, could be 5 micron, it could be 2 micron. We're only reducing the amount of particulate that could be taken to the process. It doesn't have any effect on the gases or on the moisture. Wet steam and gases would travel straight across the filter. We'd be stopping a certain percentage of the particulate. So the answer there is it minimizes the risk, it reduces the risk. It does create a significant back pressure because it can have a coalescing effect. But in the pharmaceutical sector, we don't have the appetite. We don't have the appetite for risk, simple as. So when we've got a process that requires a greater grade of steam or a better grade of steam to plant steam, we would typically go straight to chemical-free or clean steam to satisfy the requirements of the process.
Okay, thank you. I have a question here. Is there ever any reason to want condensation within the steam supply, such as for when feeding a wet steam accumulator?
Certain processes may need a particular dryness value, but on the whole, when we're talking about plant steam systems, on the whole, condensate isn't considered beneficial. We need to get the condensate away because it creates the problems with the erosion, corrosion, water hammer, because it creates issues with not having as much heat energy contained within it. So typically speaking, condensate has got absolutely no value whatsoever to a plant steam distribution network. It does if we can recover it and get it back to the energy center.
Okay. Well, I think we'll leave it there if that's okay, Dan. We're over the hour now.